Right, so yes, I want to talk to you about my PhD research on the Middle Devonian of northern Spain. We know that the Spanish Devonian is very comprehensive. You can see that we have a pretty much complete sequence of deposition through the whole of the Devonian period. This is entirely marine deposition, predominantly of limestones, all except for this bit here. The Naranco and Huergas formations of Asturias and Leon are enormous sandstone bodies interspersed with some black silts and shales, positioned slap bang in the middle of all this marine limestone. This clearly represents a major depositional anomaly taking place from the lowermost Iphelean up to the low Juvetian ages, the cause of which is unclear. We also know that the Devonian period is punctuated by a series of extinction events. There's actually a lot of them, all the way up here. The one we're interested in is the Kachak event. This takes place on the Iphelean-Juvetian boundary, or towards the top of those formations I'm looking at. Now this event is very ill characterised in Iberia, and its effects on terrestrial floras are very little known indeed. So this all sets up my study's original primary question. What changes took place during the Middle Devonian in northern Spain? Because clearly something's going on, and can any of this be related to the Kachak event, which we know was happening at about the same time? So, as I said, I'm looking at Iphelean to Juvetian ages, about 393 to 382 million years ago. Iberia is just here in this sort of archipelago, really, that also includes bits of France and Central Europe. That's round about 30 degrees south of the equator, having just broken off northern Gondwana. Devonian rocks in Spain, in northern Spain, outcrop in this large arc shape from the Asturian coast up here in the Aiguillon, south past Oviedo and into Leon, before turning east and heading off towards Palaeontology over here. They also exhibit a progression in their character as you move around here. They're very sandy in the north. There's a lot of terrestrial influence. As you move around the arc, that influence weakens. And by the time you get to Palencia, you're looking at a marine limestone with some black shale in it. That carries on all the way around. This points to there being some kind of terrestrial source off to the north, up here somewhere. This has all been very heavily tectonised in the years since. You can't really draw much from that outcrop pattern. This is where all my sites are. You can see I trace out that arc quite well, and this is them on a geological map. The Devonian sediment is picked out in shades of dark green. These four sites that I've indicated with arrows are significant sections through the formation, which are logged and sampled, and I'll be telling you all about this one in great detail a bit later on. My methods are an entirely ordinary maceration. Take your rock, clean it, crush it up, dissolve it in acid for a month or so, sieve out what survives. Heavy liquid can get rid of clay minerals, and you're left with a fine particulate organic matter. That can then be strew-mounted onto microscope slides, and you end up with something that looks like that. Now, preservation on this material is generally very good, but thermal maturity is very variable. This stuff is very dark. It's been heated up during burial, and that makes it hard to study under a light microscope, as you can imagine. So all my material has been oxidised in Schultz solution, and it clears up beautifully. You use it to oxidise things. So there's spores in here, the acrotarchs, there's all kinds of nice things to look at. I have also spiked all my samples with modern lycopodium spores, so that I can do a quantitative assessment of the fossil assemblage, the importance of which will become clear later on. What I then do with all my slides, I've got like 4 boxes of microscope slides covered in fossils, I then count fossils in them. And I have 113 samples from 20 sites, and that has generated a sizable data set containing 19,753 individual fossils identified to species level. It is this database that I am currently attempting to make a PhD out of. Let's see what I've actually found. These are the spores of various different kinds of land plants. They come in all different shapes and sizes, and they're very useful for biostratigraphy, that's the word. There are a number of very well-developed stratigraphic schemes for these, so they're very useful for dating our formation. And they also indicate terrestrial influence and a nearby shoreline. Remember, this is a marine deposit. If you find a lot of these, they must have been either blown in on the wind or conveyed there in a river. Acritarchs are marine algae of one kind or another. And if you find lots of these, you have marine influence. They usually counteract one another. Acritarchs are also useful for biostratigraphy, but in the Middle Devonian, the stratigraphic scheme is a bit coarse. So the best I can tell, I can definitely tell this is a Mid-Devonian assemblage, but I can't really tell a great deal more precise than that, unfortunately. The same can be said of Chitinozoans. These are enigmatic thingamajigs that we don't really know what they are. The best guess at the moment is that they're the egg cases of some kind of unknown metazoan, but I've never been particularly convinced by that. Who ever heard of an egg case that's not more than 0.1 of a mil long? But they do definitely indicate a marine influence, and a strong one at that, because these tend to be quite rare in this assemblage. The same can be said of Scalechodonts. These are the teeth of polychaete worms, and these are very rare in this assemblage, as they usually are. They have a taxonomy and a biostratigraphy associated with them, but it's rather too complicated for me to get into, given how rare these are in my assemblage. Unfortunately, they're just nice to look at. Right, let's see how I go about using them. This is my favourite of the sites I have, and it's not just because it's at the seaside. The Playa del Tranquero site, just here, exposes the Naranco Formation tipped on its side completely, from a lowermost contact down here, all the way over to an upper contact over here, with the formation exposed in the beach, this sand-free platform over here, the cliffs, and in the path above the cliffs, which is very handy for when the tide comes in. I spent a day and a half logging this and ended up with this. This is a stratigraphic log of the Naranco Formation at the Playa del Tranquero. You can see the bottom, more than half of it, is this undifferentiated sand block. This is expected. You see this elsewhere for the formation. The top half of it is very heavily interbedded with finer beds of siltstone and mudstone. And it's these that you get palaeontology from. This also indicates sea level change. In a rude sense, sand beds indicate shallow seas, finer beds indicate deeper water, where it's had more chance to settle out. So if we were to isolate this block, which is the bit I've sampled, and look at that, this is the palaeontology log. On this chart, green is spores and blue is acritarchs, the algae. And you can tell lots of things from this graph. As this is a quantitative count, the horizontal scale is the raw number of palaeontologies per gram of rock. And it's a lot, in the tens of thousands. Luckily I didn't have to count all of them. But you can see that the abundance of the formation varies wildly over this period of time that this represents. This is probably due to either ecological influences or its depositional effects. Probably the depositional environment wasn't conducive to their preservation at certain times. But you can also look at the proportions of these things. Here, for instance, you've got about 1 part acritarchs to 2 parts spores. That's a lot of acritarchs to be found in one place. There's a lot of marine influence here. It's probably quite out to sea. Here, though, there's less acritarchs and a lot more spores. This means that the sea level must have fallen. The shoreline has prograded out to sea and got closer to this site, meaning that the land-based spores are nearer. The source of them is nearer, and you get more of them. If you follow that logic through, sea level is going wild, up and down, all through this time period. Speaking of time, that is rather important to my next part. This is the Devonian time scale, and this is the bit that we're interested in, from the Polygnathus costatus costatus, conodont zone up to the P. varus zone. Now, conodonts, as I'm sure you're aware, are the mouth parts of early chordates, and they have a very, very well-defined biozonation scheme that we can use to help date rock formations. Unfortunately, you don't find conodonts in my formation, they're just not there. You do get them in the limestones above and below, though, so we can bracket the age of the Naranko with some accuracy. The bottom of it is the bottom of the P, PC costatus zone. The top of it is lower P. varus zone, somewhere up here, in the Givetian. This is the Givetian here. The problem comes when we try to marry that with my palaeontology results and the spore biostratigraphic schemes. This charming customer is Geminospora lemurata. This is quite a complex spore, probably produced by some kind of progymnosperm. And it has a very well-defined age of first occurrence. It's very useful for biostratigraphy, and it defines its own zone in, imaginatively called the Lem zone, in a number of schemes, and that occurs just here, in the bottom of the, or lower P. hemianzatus zone, just inside the Givetian. Problem is that I find G. lemurata all the way down here, in only my third sample that I have, and the bottom two are very, very impoverished. This means that this formation cannot have been deposited at a regular speed. This point is fixed, this point is fixed, this point does not tally with the top and the bottom. This is a scale of thickness. If this was a true scale of time, so it matched up with this, the formation must necessarily look a lot more like that. We've already established that this part of the formation records sea level change in great magnitude and with great frequency. Now we can say that it occurred in a very, very short space of time. This could be as little as 400,000 years. Sea level has gone absolutely wappy, up and down, up and down, up and down, all over the place. This must have caused some kind of effect on the life of the area. That is what I was hoping to look for, but it seems that the conditions conducive to preservation of these palaeontomorphs simply did not exist before the Kachak event took place. The Kachak is on the Arphelian-Givetian boundary, in line with this. The two events must be connected. The Kachak happens, all of a sudden all this goes on. You've had steady sand deposition for, what, like 4.5 million years, and then suddenly all this happens. And because there's no samples from before the event, I cannot compare them, and it's really, really frustrating. That's what I was hoping to do, ultimately. But we can still draw some early conclusions from this. We can see that the Naranko and Huergas formations contain an incredibly rich assemblage that hasn't really been studied much, in all honesty. The abundance varies wildly, and we can see that the formation was deposited at varying rates over time, and probably diachronously. I've not said in the slides, but some of my other sites from further south don't have that big sand block at the bottom, and G. lemurata comes in almost immediately. These must have been deposited later, and this corroborates the idea that there was a sedimentary source in the north, and more southerly sites took longer to receive all that terrigenous input, all that sand. The limestone deposition continued for slightly longer at these sites. With that, I'd like to draw this presentation to a close. I'll be happy to take any questions, and I'd like to thank you all for listening.